Okay, in today's lesson, we want to review the basic function graphs. Before we do that, let me remind you that we have quizzes that are due this week and every week. You can check for your due dates on Pearson Math Lab. There are also the questions or even explanations in your e-text if you're interested in using that. A reminder also that you should have these notes printed. And if you don't have them printed, then you're writing down everything I talk about in these lessons, so you have notes for your revision. It's also true that when we write things down, it helps us to learn, to understand better, and to remember. So today in our looking at basic function graphs, we're first of all going to create a table of values and use that to graph the functions. I'm hoping that you're going to memorize the 3 key points on each of those graphs, memorize the domain and range for each graph, and then of course memorize what the graph itself looks like. We're going to start with the constant function. That can be written as the equation y equals c. All of the graphs we're looking at today are function graphs. So instead of y, we could be writing f of x equals. So this is a function where y equals c, where c is any real number. You should know what this means when we talk about an equation, y equals some number. X could be -1, y is c. X could be 0, y is c. X could be 1, y is still c. In fact, x could be any real number. So if we decide to let this be c on our y-axis, then we would have the points 1c, 0c, -1c, and we see that this is the graph of a horizontal line. I hope you knew that already. Why don't you pause your video and write down the domain and range for this function graph. I hope the domain is obviously the set of all real numbers, but I don't have an interval for the range. It's not going from a number to another number. It's simply the set of one number, in this case, c. Our second function is a linear function where we have that basic linear equation, y equals x. Why don't you pause your video and graph that function? We see that x and y are always the same value. Y equals y equals x. But what you should know is that these 3 points are not enough to tell you what this graph looks like. We should always check a few other points because we're going to find as we go through these function graphs that having the same 3 points occurs over and over again. So we also need to know what the graphs look like. In this case, we knew it was a linear function that we were graphing. Why don't you pause and write down the domain and range? I hope you know that the domain and range for all diagonal lines is the set of all real numbers. It doesn't matter which key points you memorize, but you're going to see that I often choose to let x equal -1, 0, and 1 for our key points. I hope you're familiar with the quadratic function y equals x squared. You should know what this graph looks like. Let's find some ordered pairs for it using -2, -1, -1/2, 0, 1/2, 1, and 2. Pause your video, fill in the table, graph the function. I chose a few extra values for x beyond simply -1, 0, and 1 because we wanted to be clear about the shape of our parabola. You can notice that as it gets closer to 0 here, it's a little bit flatter. It doesn't go straight up in a straight line. We have some exponential growth going on here. You can pause your video and write down the domain and range for this function. And while the domain of all quadratic functions is the set of all real numbers, the range, of course, will change depending on where the vertex is and whether our graph opens up, like this one, or down. Y equals the square root of x. That's our square root function. And we see if we let x equal -1, we're going to have no real solution. We can't use negative numbers inside our square root function. So we start with x equals 0. The square root of 0 is 0. The square root of 1 is 1. Pause your video, find 2 other points, and finish graphing this function. I hope you let x equal 4. We know the square root of 4 is 2, and x equals 9. The square root of 9 is 3. So we have this increasing function heading towards positive infinity. Pause your video, write down the domain, range, and 3 key points. For the square root function, the domain and range are both the interval from 0 included to infinity. And I use the ordered pairs, the first 3 that have integers, 0, 0, 1, 1, and 4, 2. It doesn't matter which set of ordered pairs you use, as long as they give you a good sense of what the graph could be. So when we look at the cube function, y equals x cubed, we see that the 3 main points are the same 3 ordered pairs on our linear function. We're going to need to evaluate more values of x in order to get a good sense of what this graph should look like. So let's try -1/2, +1/2, -2, and +2. Pause your video, finish graphing this function. Does your graph look like this? I hope so. You should notice that again, close to 0, the graph is quite flat before continuing exponentially to positive and negative infinity. You can see why it's important that we memorize the shape of each graph, because looking at the ordered pairs is not always going to be sufficient. These 3 key points were the same key points on our linear function. So we need to know that the graph of x cubed is different. Even the domain and range is the same as the graph of our linear function. So when we're looking at the cube root function, we see that x can equal -1. The cube root of -1 is -1. But these 3 key points are exactly the same as our cube function points and our linear function points. Can you find some more points and finish graphing this function? I hope you use positive and -1/8, positive and -8. We can find the cube root of each of those numbers. And I don't think I've mentioned before that it's important on these graphs that you have your arrows on the end where it is appropriate. The graph doesn't stop at the ordered pair 8, 2. It can keep going to 27, 3 and all of the points in between. The domain and range is again the set of all real numbers, and our ordered pairs, the same ones we've used for the linear function and the cube function. We talked about absolute value when we were solving inequalities. We said that the absolute value of x has two pieces to its definition. It equals x if x is greater than or equal to 0. So for example, when x is 0, the absolute value of 0 is 0. When x is 1, the absolute value is 1. When x is 1/2, the absolute value is 1/2. We said that if x is less than 0, then the absolute value of x is the opposite. So when x is -1, then our absolute value is +1. When x is -1/2, the absolute value is +1/2. And so we have this graph that forms a V. Why don't you pause your video and write down the domain and range for this function? Notice that the domain, range, and the key points are exactly the same as they are for our quadratic function. So again, you need to know the shape of this graph as well as these characteristics or properties. Finally, we have our reciprocal function, y equals 1/x, where x cannot equal 0. Let's work through this graph together. We know that x cannot equal 0 here because then the denominator would be 0. This gives us a vertical asymptote. The equation for that asymptote is x equals 0. We're going to represent that asymptote with a broken line at x equals 0. Remember, when x is equal to 0, this equation would be undefined. So the graph cannot touch or intersect the asymptote. So when I look at values of x, I could say that x equals not 0, but maybe -1. That would give me -1. If x equals -2, -1/2. -3, -1/3. -4, -1/4. I can see my graph getting closer and closer to y equals 0. So the question is, what value of x will make the graph equal 0? So when does y equal 0? Well, I hope you remember that the only way for a fraction to equal 0 is if the numerator equals 0. But we don't have a 0, we have a 1. That tells me that this is not possible. The graph is never going to equal 0 at y. So in fact, this gives me a horizontal asymptote at y equals 0. Now it is possible in other graphs to reach 0, but we're not going to for this one. So we see that it's getting closer and closer to 0, but it's not going to touch. What about in this space here between -1 and 0? If we let x equal -1/2, we have y equals 1 divided by -1/2, which equals -2. Here, we're getting closer and closer to x equals 0, but not touching that vertical asymptote. When x equals +1/2, we're going to have +2. X equals 1, +1. X equals 2, 1/2. So in both cases, getting closer and closer, but not touching our vertical asymptote, And then here, getting closer and closer, but not touching our horizontal asymptote. So in this case, I wouldn't say we have 3 key points. I would say I have 2 key points at -1, 1 and +1, 1, but that we also have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. The domain, well, we know the domain because this tells us that x can't equal 0. So we can say from -infinity to 0, union 0 to infinity. We also saw that y can't equal 0. So our range is also from -infinity to 0, union 0 to infinity. Take some time, make sure you memorize these graphs. You know the domain and range for each of them. You know the picture for each of them.